Welcome everyone to the public lecture as part of the LMS-Bath Symposium on the mathematics of machine learning. It's with great pleasure that I would like to introduce Carola-Bibiane Schönlieb to you. She's a professor of applied mathematics at the University of Cambridge. There she heads the Cambridge Image Analysis Group. She's also the director of the EPSRC Center for Mathematics in Healthcare and the director of the Untitled Chapter Institute for the Mathematics of Information, as well as a fellow of the Alan Turing Institute. And I can see on your slide, Carola, that there's another icon, another logo that I don't recognize at the bottom right, and you probably need to tell us in a minute what this is. Carola also received like a number of prizes over the last couple of years. To name a couple of highlights, in 2016 she received the Whitehead Prize of the London Mathematical Society. In 2017 she received the Philip Leverhulme Prize, and in 2019 the Calderon Prize for Inverse Problems. Next to all her successes in research, she also has devoted a lot of time to do outreach. And so in previous public activities, Carola told us if mathematics can make you fly and how to make stuff disappear using applied mathematics. So I'm very much looking forward now to look with Carola into the black box of deep learning.
Thank you very much, Matthias. A really, really kind introduction. And the EWM is the European Women in Mathematics Association, which I have been convener of until recently, actually. So yeah, so that's why this is also on the slide. I'm very, very deeply connected to them. Okay, so what I usually do before I start such a public lecture is to ask people what their backgrounds are. Of course, this is now not possible, really. So therefore, I really ask you to raise your hand, your electronic hand, write something in the chat throughout the talk, and maybe Matthias, since I for sure forget to look at this, maybe you can just interrupt me. So really feel free to interrupt me anytime. Okay, so this is really to convey some maybe interesting aspects behind mathematics for deep learning. So what I want to do in this talk is to lift a few mysteries behind deep neural networks, while at the same time appreciating the fact that at the moment there are a lot of workshops, conferences, meetings happening in mathematics, which have, you know, mathematics and machine learning and deep learning in their title. Therefore, you might appreciate the fact that there are lots of mysteries that I will not lift, which are keeping a lot of us busy at the moment, and which also provide us a really interesting time as mathematicians. Okay, so let's get into it. What I thought I'll do at the beginning before I start with the actual deep learning talk is to tell you a little bit about myself, since I believe a public lecture like this should also serve as a way to be role models for other people who might consider a career as a mathematician maybe, and who will be happy to know that we are just very normal people. So, right, so this is me. I'm an Austrian mathematician working in Cambridge. I studied in Austria, worked in Germany, the UK, and Austria. Visited lots of places in my lifetime as a mathematician so far, for longer or shorter periods. My work has brought me to the US, to South America, to Japan, to all kinds of places in Asia, to lots of different places in Europe. So it's, I would say, something that definitely adds to the advantages of being a mathematician. My passion is really for developing new mathematics that are directly inspired by applications. Most of the work that I do is very, very close to applications. And as you have just heard before, I'm also very active in women encouragement in mathematics, since there is still a lot to do. My own research is in the mathematics for image analysis, image processing, medical imaging, and so on and so forth. And what I like is to travel. I like dogs. This is another me here, not as a mathematician. I like hiking. And I also like in the work that we do, in particular in this more modern idea of applied mathematics, I really like collaborations. I really like to discuss and work with people, which is something I want to stress, because very often the picture that people have of a mathematician is that they are alone in the office in front of a piece of paper, and that's it, and are just deeply thinking, which is definitely also part of what we do, but not just that. Okay, so this actually, all of this Matthias has mentioned. So let me skip over this. Maybe just to show you that this is what I mean with collaboration. So the group in Cambridge that we have, the Cambridge Image Analysis Group, consists of about 20 people, half-half split in postdocs and PhD students. And they're actually all kind of happy about what they're doing. So, okay, so let me also skip over that, because that's not too important. I told you that we develop image analysis tools for all kinds of different applications. So let me actually go immediately to what I want to talk about in this public lecture. Okay, so what I do is I first convince you that it's worthwhile to, or I remind you, I guess a lot of you are already convinced about the success behind deep learning, and that this has just had a huge impact in all kinds of areas in our life, technology, and so on. Then I give you a mathematical characterization of neural networks that helps us at least understand what is happening when I take an input and I put this through a neural network and I get an output, what is happening in between. And then I'll say a little bit about things that, concepts that mathematicians have thought about in the context of deep learning, and trying to look into this otherwise pretty hard to understand mechanism of deep learning. And I'll give you a particular example that we have used where we parameterize neural networks as discretizations of differential equations. And if you don't know what this means, just hang on, you will find out in a moment. And this is, by the way, also joint work with Matthias, who introduced me just now. Okay, so nowadays, the world around us is really dominated by the fact that we are collecting data all the time. Lots of data, large-scale data, high-dimensional data, quite diverse data sets, data types, in all kinds of scenarios. And hence, there is a huge need for automated tools to interpret them, to interpret these data sets, and help us actually make use of them in making decisions, in automating things. Think about self-driving cars, for instance, or things like that. And this is just to show you that this data, so what I just said, is represented in these 4 V's here. So there is a lot of data, there is a huge volume of data, there is a variety of different types of data. This data is being collected at increasing speeds, and it is also full of imperfections. It's full of uncertainty, because of noise and things like this. So methodologies that we develop to analyze this data and to use it to our advantage need to take those 4 V's into account and take advantage of them. And this is kind of what deep learning learned to do. So very briefly speaking, data science, and in particular deep learning, is not about the data actually, it's about extracting information from this data in an automated, robust and efficient manner. And this data, as I said, or in particular this information, can come in various different forms, can come in the form of classification. This is, for instance, a classification of an image into different types of vegetation. Could come by saying, I have an image and I want to detect and outline particular objects in this image, which is called segmentation. Could come in any type of quantification I want to do on the basis of data. Okay. Any kinds of statistics I want to derive from data that is given to me. And so all of this actually, all of this is based, why this is possible with all this messy data with the 4 V's, huge volumes, variety, uncertainty, noise, all of this is possible by developing methodologies that can detect patterns in this data. So all of machine learning, all of data science is about detecting patterns in data. And these patterns help us to extract the information we are interested in. Okay, and here is just a representation, an example of such a pattern, which could be the geometric shape of trees. This is a segmentation example of trees from so-called LiDAR data. So what is deep learning? And this is just high level. I start very high level, give you some examples, and then we go a bit more into the nitty-gritty details. So deep learning is a subset of machine learning, which in itself is a subset of artificial intelligence. And you can see that plotting this a little bit against a timeline here, that deep learning really arose in the last 10 years or so, really made a huge boom in this last 10 years. The reason being that we have increasing amounts of data. Okay, so remember the 4 V's, we have a lot of data. And we have now the computing power. So this emergence of GPUs has had a huge impact onto actually being able to train these neural networks. Huh? So again, deep learning is a subset of machine learning in itself, is a subset of artificial intelligence. What are all of those? So artificial intelligence here is a program that can sense, reason, act, and adapt. Machine learning are algorithms whose performance improve, their learning improve as they are exposed to more data over time. And deep learning is a particular type of such learning algorithms, which are represented by these multi-layered neural networks. And in particular, what is written down here is that they learn from vast amounts of data. So this is a special thing about deep learning, because they have so many parameters that they usually work extremely well. You can do lots of things if you have enough data to train them with. So success stories, and for sure, you know a lot of these, and maybe you know a lot of the details behind these much better than I do, but let me just go through a couple of them just to get us in the mood of actually trying to see what is happening behind the scenes here. Alphago is one of the kind of early success stories of deep neural networks. And here I'm just quoting from the Alphago website. In October 2015, Alphago played its first match against the reigning 3-time European champion, Mr. Van Hooy. AlphaGo won the first ever game against the Go professional with a score of 5-0. Further, over time, AlphaGo improved and became increasingly stronger and better at learning and decision making. This process is known as reinforcement learning. AlphaGo went on to defeat Go world champions in different global arenas and arguably became the greatest Go player of all times. Okay, cool. So it can play games. This is super impressive because playing Go, I mean, is super complex, and there is a reason why people spend their careers on perfectionizing their Go play. But it's a set is a finite amount of rules, right? So in a way, it might be kind of understandable that a neural network trained with a finite amount of data might be able to capture something like this. Still, it's impressive. But natural language processing is another example. Those of you who have something like Alexa or Siri or something like this, this really works because there are intelligent mechanisms, so there are mechanisms, machine learning mechanisms behind that, which are trained and which also continue to learn what, you know, the essence behind what people are saying and how to react to that. And so I told you I come from imaging. So for me, imaging is also one, or computer vision, image analysis, image processing is one big thing where deep learning had a huge impact and gave really impressive results. And so what you see here is from, so the ECCV is a computer vision conference, one of the main computer vision conferences, research computer vision conferences. And this is a contribution from 2018. And what you see here is on the left. So this is kind of real time showing you what the neural network is doing. Okay, so this is the input to the neural network on the left. This is the output of the neural network on the right. And so, I mean, maybe it's self-explanatory, but what you see is that when you cover certain parts of the face, that the network comes up with plausible suggestions of what should be in these wide areas, and that's super impressive. I myself did actually my PhD on image in painting, what is called image in painting, which is kind of what is behind this, and I can tell you this is super impressive. Yeah. Okay, this is a really complicated example, complicated problem. Editing, similar thing, okay? Although here editing means you give some guidance of what you want the neural network to put out. And again, this is, I mean, it's kind of fun, but it's super impressive actually what can be done. This is my last example, I promise, in the computer vision kind of examples. But so this is deep learning for style generation. So here, the idea somehow is that I have this what is called here source B, and then I have here another source of different images. And what I want to do is I kind of want to interpolate between them. So I have a kind of smooth process that accentuates different features, different styles from these different images. And so all of these images that you see here, they are actually computer generated. So they are generated by the neural network. So this is kind of cool, isn't it? So. And I should thank here one of my postdocs, Angelica Aviles-Rivero, who helped me find these cool examples. So thank you, Angelica. Another area where deep learning has increasing impact and also increasing success stories, although it hasn't yet totally entered clinical practice because of good reasons that we will see in a moment. It has a huge potential to help healthcare in different areas, in diagnosis, prognosis of disease, patients coming in trying to find out what is wrong with them. So apart from deep learning, any kind of data analysis has this potential because it can take into account not just, let's say, one snapshot of the patient, but it can actually integrate various types of data over time of this particular patient. So it's much more powerful to do this, and it can also put one patient in context with a group of other patients which might look similar, and so we can learn from that. Anyway, deep learning has a huge impact. Again, think of a radiologist trying to interpret an X-ray, trying to find a tumor, a lesion, things like this. Deep neural networks can help you to do that. The same thing with high throughput imaging that is used for drug development, for instance. Again, deep neural networks can help you to interpret these millions, billions of images that are being used in this context. And it can also help you, by the way, to design clinical trials and things like that. And in particular now, in this situation that we are in with COVID, there are people, and there are initiatives, increasing initiatives that are being made possible because of powerful machine learning approaches like deep learning, which can help us to understand diseases in an emergency situation like the one we have now in a much quicker way than we could in former days, just manually. So this totally has a huge potential in the healthcare industry. Okay, so now let's go to the mathematics. So now we've seen a few examples of what deep learning can do. Let's look at a few examples. Is there anything so far? No. Okay. All right, so ingredients of deep learning. What are the ingredients of deep learning? Data, okay. The other ingredient is the network. And another ingredient that I'll show in a moment is the training of this network, of course. Huh? So what is happening with a deep neural network? So a deep neural network, let's say once it's trained, okay, and I'll explain what training means. It takes as an input some data that you have and that you want to do something with this data. Let's say you have a data set of faces and you give the network a face and you want to find a match to a face in your database because you want to find out who this person is, for instance, which is called the classification problem. So the output of this neural network, once you take a face like this, should in this case be a classification to another person, to a name. Or in other cases could be classification into the typical thing we are seeing all the time, dogs, cats, and so on and so forth. Another output of a neural network could be what we have seen just now with these computer vision examples, could be an edited, restored version of an image. So the input is an image, and the output of this neural network, once it has gone through these complicated building of nodes and connections, the output is also an image. In medical diagnosis, it could be that the input is something that you've measured from the patient, and that the output is a diagnosis, prognosis, again, classification or regression. You can formalize it like this. Or in the case of playing games, for instance, like in Alphago, it could be the recommended next move in a game, for instance. Okay. Okay, so now let's try to look a little bit inside of this, because I want to get rid of this blobs and connection picture very soon. Okay, so let's look a little bit more into this. Okay, and so this is now a 3-layer neural network. where I count the input layer and the output layer also towards these layers. Okay, so it's a 3-layer neural network. I start counting at 0. So my input layer is layer 0. My output layer is layer 2. Okay, so input, we've said, can be all kinds of things. What I abstractly think about the input as a vector with entries that are here, the entries in these blobs, in these nodes. Okay, and these entries, think of them as real numbers. These could be, again, depending on your application, could be the values of different variables that you have in your data. Could be the intensities in the pixel intensities of an image, could be different things. Okay. Okay, so you take this and now you want, now you send it through the network. And so what is the network doing? Very roughly speaking, what the network is doing, it takes this input vector and it applies a number of linear and non-linear operations to it, where the typical form of such a setup is that when you go from one layer to the other, this vector x here is multiplied with a matrix. Here you have the matrix. Sorry if this is too small. This is the matrix, okay, of a certain dimension. So you multiply this vector with the matrix, and this matrix is also called the weight matrix. And then you add another vector, which is in deep learning also called the bias. And then you get, so out of this, the result is another vector, okay, whose dimension depends on the dimension of your matrix W. I'll show you this in a moment in a bit more detail. And then you have, so this is all linear so far. And then the last thing you do is to apply a so-called activation function, which is a nonlinear function. The typical activation function that many of you have in mind is ReLU, for instance, which is a thresholding operation. And here I'm using the smooth version of this, which is the sigmoid function. Okay, so think of this again as a thresholding. So if things are smaller than 0, you set them to 0, and otherwise you leave them as they are. And this nonlinear function is now applied to this vector component-wise. Okay, so as an example here, to understand what is here in the next layer in this first node, okay, in the first entry, it's the result of taking the first row of this matrix W and multiplying it with the vector x, right? This is what I've written down here. And then I add the first component in the vector B. Okay, and this is telling me what is happening now in this next layer, and then you do the same going to the next layer, and then you do the same going to the next layer, and so on and so forth, where every time you go from one layer to the other, these W's can change. Okay, so these are free; they are not the same. So the W's can change, and the B's can also change. Okay, so I think that's what I wanted to say here. So I hope this is not shocking you too much now, this jump, but what is happening now is that I want to write down what this means if I iterate this process, okay, of multiplying with W, adding B, and applying this activation function. So this we have seen before. This is my matrix. So my matrix is K here. The index K here stands for the layer. So this is the matrix for layer K. This is the bias for layer K. Okay, and this is my input that I have for layer K. So before looking at this here, let's look at what I have here at the bottom, where I want to connect what I've shown you before in the previous slide with this iteration going from one layer to the other for a 4-layer neural network. So now I consider 4 layers, and I take as an input X. Okay, so input is X. This is my 0 layer. So after sending X through the first layer, what I get is this. This we have seen before. Now this is my new X, right? So now I take this and I do the same as I did for X. I do this now for this guy here. And what I get is this. Okay, so I take this, I multiply it by W, I add B, and then I'll apply the activation function component-wise. And I do this also for the next layer, and then I'm happy, and I'm at the last layer, and I compute and I record this as my output. So the last layer is now the result is phi of X, and this is the output. This is the output of thinking now of this neural network as a function. This function takes an input X and gives out phi of X, which is, let's go back a second, which is this which are the entries in this last layer. Okay, and you can also think of this as an iteration. Okay, so you start with your iteration in the first layer, in the 0th layer with X0. Okay, so this is again my index for the layer. And then this is my sigmoid function. Okay, now I'm giving you the equation, and then I iterate for k equals 0, 1, and so on and so forth until capital K, which in the 4-layer network would be 3. Okay, remember that I start counting from 0. I evolve like this, right? So every output of a layer is taking the input from the last layer, multiplying it with W, adding B, and applying the activation function. All right, good. So this is what I'm doing, and a very nice, by the way, work that really breaks down the essentials behind deep learning in a very, very nice and clean mathematical way is a recent review paper by Catherine and Des Hyam, where actually Catherine is one of the organizers of this workshop. Okay, so this is where we are, right? So now we have just written this down in terms of an iteration. What else? Okay, so this is what the network is doing. Okay. So what does training a network mean? So training a network or deep learning, okay, in other words, is about finding now the best such weight matrices W and biases B, so that given this training data, which consists of pairs of inputs, input images, like these ones, for instance, okay, input images and associated outputs of the network. Okay, think of the network output being, for instance, a classification. So the yi's being a label that corresponds to what the image shows: airplane, automobile, bird, and so on. Given this training data, I want to find the best W's and B's such that they are optimal with respect to a particular criterion I have, that they're optimal with respect to bringing the output of the network, so my phi of xi, close to the labels yi. Okay, what I want is that my network spits out something that approximates yi. And this is what I'm basically optimizing these W's and B's for. Okay, so what does this mean? I'll go with you there, but bear with me for a second. So what have I written down here? So this is the sum of loss functions. So these criteria, these optimality criteria, these distances between yi and phi of xi are called loss functions. And so I add up the loss functions for all of these elements that I have in the training set. What I want, and so this sum means that I add all of them up. So what I want is that for the elements in my training set, that the output of the network is close to the given labels. Making this a bit less mysterious, a particular choice of loss function that is very often used is that I say that the output of the network is close to the true labels in my training set in a least squares sense, for instance. Again, think of this as the Euclidean norm. So the Euclidean distance between the two. Okay, so I want this to be small. Now, of course, the YIs are not the words airplane, automobile, and so on and so forth. So what are these Ys? I mean, they should be comparable to something that the network can produce, right? Which is a vector with values inside. So what are they? And again, this depends on how you set things up. But one way to set things up is to say, my YI, let's say my Y1 is standing for airplane. And this means I have my output of the network, my vector Y, is a vector of length, number of labels that I have for the different images I have in my training set. And I put a 1 to the particular label that is present in the input, okay? So if X is an airplane, then phi of X should be 1 at the first position and 0 everywhere else. So it's an identity vector with where the 1 is standing at the respective place that characterizes airplane, automobile, bird, and so on. So this would be the one for airplane. This, for instance, would be the output for automobile. Or this would be, for instance, the output for dog, and so on and so forth. Okay. Okay, so are you still confused? Another thing or another way to think of all of this is not through classification, but first maybe think of it as a regression problem. Because regression, for instance, linear regression, like in this case, a lot of us are familiar with. So the problem is much simpler here. My X, my input, is one-dimensional. It's just the value for the tumor size. Okay, this is a medical example now, a made-up example, by the way. Tumor size, and the output of the network is now not a classification, but is a probability for the tumor being benign or malignant, okay? Or the probability for being malignant, yeah? And what you see here, the little stars, is the training set. So these are the pairs that we measure between my tumor size X and the output, the probability Y of being malignant. So what the network could do, for instance, is to, in order to now deal, to extrapolate, kind of, to use the information that I have through this training set, to use that for new tumor sizes, for new samples that come in terms of tumor size. It could approximate this by a linear regression, for instance. And then I say that if I get a sample with a tumor size like this, the probability of this being malignant is whatever is on the value on this line, for instance. The corresponding classification I get by cutting off, okay, by saying if the probability is larger than 0.1, the tumor is malignant, and otherwise it's benign. Okay, this is linear regression. Now, deep learning, you could think of, is a highly nonlinear regression in very high dimensions, not just in these 2 dimensions. And so why is this necessary? Well, because the world is not linear, unfortunately. So there are lots of places where we need to be able to approximate things in a nonlinear way. Where this is just, again, a simple example made up, again, actually, by the way, by Matthias here, where we see 2 classes, data points in 2 dimensions of 2 classes, which could, for instance, in this case, never be separated with a linear classifier in this particular way as they're represented here or here. Yeah? So we need something nonlinear. A few more things. I've shown you the sigmoid function. Just to say again, a very popular activation function is ReLU. It's this rectified linear unit, which is a thresholding function. There are lots of other degrees of freedom in these neural networks. One very prominent one is the loss function. So the loss function that determines somehow the optimality of your network parameters is always chosen depending on the thing you are on, the problem you want to solve, on the application you want to solve. So this will be something different if your output is an image versus the output of your network is a label, for instance, or something else, or a probability. Yeah. So these loss functions, there are different types of loss functions. I've just shown you these least squares fit, but there are different ones: cross entropy, L1 loss, and so on and so forth. The other thing is that in a lot of deep learning applications, these weight matrices, W, are not just full matrices, but they are structured. And this is good, that this is actually sufficient, because you can imagine that if you have these full matrices representing going from one layer to the other, that this is a huge, is computationally a huge thing that you have to deal with memory-wise, and so on. So a lot of times what you hear is the word convolution, convolutional neural networks, and these are structured matrices which are sparse, which are, for instance, just given by in each row of your matrix you have just 2 entries, which are so these are banded matrices with diagonal and sub or subdiagonal being having entries other than 0. Okay, so structure is nice because it gives you less parameters, and is also somehow intuitively a good way to think of network operations, as they make connections of what we might think the network should be doing. So in a way, if you have an input, and in this case I'm going back to images because they're visually it's visually kind of intuitive what is happening. If you take an image as an input, and in the end you want to classify this image, you might think that the network is doing something with this image, is extracting some features, some patterns in this image that help you to classify it in the end. Yeah? And so they're thinking of these matrices as in this structured way makes a lot of sense. So think about, for instance, if your input vector X is multiplied with a matrix like the ones I've shown before, just one row of them. So 1s in the diagonal and -1 in the subdiagonal, and otherwise 0. If you multiply this with X, what you get is a vector with differences between consecutive entries. Now, what does this mean if you think of your vector X as a one-dimensional function that plots against a coordinate a value? What this kind of means is that you're taking a discrete derivative of this function, right? Again, think of it like this: if your X, if the vector X is just a concatenation of pixel intensities in an image, where I go from this image to a vector like this by just storing the pixel values row-wise in a vector, okay? Then you could think of applying this operation as something like an X derivative to this image, right? So you take differences. If this is, again, if I look at one row in this image that I've put into this long vector with lots of rows in this vector, if I look at one row, the function like this, take these differences, you get something like a derivative, a first derivative. And then you can instead of plotting the image intensities, you could plot these differences and you get something like this. So what this shows you is that this is highlighting, accentuating certain features in this image. This is a very simple weight matrix now, but it's by the way something that has been around in image processing for ages. And in a deep learning context, of course, the entries here, I wouldn't give you the entries. The neural network is finding out what the good entries are, okay? But this is just showing you that it might be a good idea to model this as convolutions. Okay. Now, this is only half of the story, of course, because now I told you that we need to minimize, we need to find a small value of this loss function. We need to find W's and B's such that this loss function is small. And this is called optimization. So what we need to do is we need, if we write down this loss function here, this is again what we had before. And now what I do is I just summarize my free parameters in the network, the weights and the biases here in this parameter vector theta. Again, I do the same thing as I did before with the image. I take all the entries in the matrix. I take in all these different matrices. I take the entries in the vectors and I concatenate them, and then I have a vector theta, which is my parameter vector, okay? And so what I want to do is I want to find now a theta that minimizes this loss function over the training set. Where in the loss function, I'm comparing my given labels, let's say, my given outputs yi, with the actual outputs that this network is producing, okay? So how do I do this? If everything is smooth, okay, like if I use the sigmoid activation function, things are still smooth. If everything is smooth, I can use something very classical in optimization. I can use, for instance, gradient descent, and this is indeed what is used a lot in training neural networks. So training neural networks, by the way, now really means that you minimize this, you solve this minimization problem, whatever this means exactly. You find a theta that in some way minimizes this loss function. And so gradient descent means you start with an initial guess for your theta, and then you go look at this function here. It's nice and convex. You start at the theta here, and then you compute the derivative of this function. Of course, this is again very nice function because it's very low dimensional. So we start here at this point. We go in the negative. So we compute the derivative of this, and the derivative of such a multidimensional function is given here by the gradient. This gives you the steepest ascent or descent of this function. Okay. And of course, I don't want to go up, I want to go down. So I go in the direction of the steepest descent, which is given by the negative gradient of this functional. And I go as far as this theta, sorry, not theta, eta, this parameter eta is taking me, which tells me how far I should go from my initial guess to the next point. Okay, so this is the gradient of my function, and I'm going in this direction. And with this step size. And this step size, by the way, in deep learning is also called the learning rate, okay, just to make a connection to that. Now, right. Now, backpropagation is another thing that pops up in deep learning. And that pops up because taking this derivative is not simple, because this f depends on a very complicated thing, which is called a neural network. And so computing the derivative basically means you need to apply the chain rule and optimization. And this is kind of called backpropagation is a very efficient way to do this. Okay, good. So let me go on a little bit. The challenges. So this is now it gives you an idea of what is behind this. What are the challenges? Well, first of all, so why can't we, this looks simple, right? We have a function, high dimensions, we minimize it, we have some implicit dependencies on this network. So what? Well, the problem is that there are too many degrees of freedom, millions of free parameters, super high dimensional. is a complex concatenation of diverse mathematical constructs. Now I've shown you the plain vanilla simplest version. There are all kinds of things, skip connection, normalization, dropout that people are talking about. It's very high dimensional and it's a non-convex optimization problem. If things are nice and convex like here, then that's fine. But if things are non-convex, how optimal this is, what you get, the parameters is not easy to understand. And so deep learning is influenced by all of this, as well as the quality of the training set and the optimization used. So in short, this is super complex and messy. So why is this a problem? Why is black box a problem? Well, if you don't understand how deep learning works, it remains a kind of black art. The ones of you who have trained neural networks before might appreciate the fact that it's not a straightforward thing to do. It's not that this works like magic, but it's actually quite hard work to get a neural network do what you want it to do. So you can do this by trial and error, or if you understand it better, wouldn't it be wonderful if you could do it in a systematic way? There is also a safety danger because there are examples, and let me just go there. There are examples where people have systematic ways to fool neural networks. So you have trained your wonderful neural network to classify images of animals to different animal types. And then someone comes along and adds something that you don't even see, right, to the image. You don't even visually see it. And it gives you a totally different classification. It screws up. And the bad thing is that there are systematic ways of creating these perturbations. So that's not nice. And it's in particular not nice if you have sensitive applications where it's about life or death, right? That decision of a self-driving car, for instance. Okay, so opening the black box, and now unfortunately I need to be a bit quick. Matthias, how much time do you give me?
So maybe like another 7 minutes.
Oh, that's really kind of you, thank you. Okay, so opening this black box is therefore worthwhile, but it's hard and it's tough. And we had a whole week of talks about trying to do something like this. There is this quote that people are using in this community, which is from 2007, from a machine learning conference, 2007. It's from Google's Ali Rahimi keynote speech. So this is a machine learning conference, and in this conference, the keynote speaker said, learning, deep learning has become something like alchemy. It's not science anymore, it's alchemy. And he got standing ovations for this. This was at a machine learning conference. So this tells you something that also not just mathematicians like us want to understand what is happening, but also machine learners want to understand what's happening. There are many open questions. Why does training of neural networks work at all? Why do neural networks generalize and not overfit? These are highly overparameterized models. You would think that if you have a training data set, they should totally just overfit to this. But and they sometimes do, by the way, but they not always do. So you can actually make them work. How can these instabilities, these systematic ways of fooling the neural network can be overcome? We know already some ways how to overcome them, but then the accuracy of the neural network predictions goes down. So how can we do this better? And there are all kinds of mathematics that are used in this context. Again, look at some of the lectures that are being recorded from this week's workshop. Approximation theory, statistics, optimization, mathematical analysis, functional analysis, differential equations, probability theory, algebra, topology, geometry. There are so many different ways how you can attack the problem, and still is super hard, and still we are struggling. Right, so let me give you one way. I hope I'm not too quick here now, but I think a lot of what I need here we already know. Okay, so I go back to my representation of the neural network. This is my 4-layer neural network. We said it's a concatenation of linear and nonlinear operations. Good. And we also said that I can write it down as an iteration like this, right? You start with your input, and then for the 4-layer neural network, you iterate for k equals 0, 1, and 2 to get an output like this. Okay, good. Next, let's change this iteration a little bit. Let's change it. Why not? I can do whatever I want in my network. Let's change it that when I go from one layer to the other one, I don't just take the input, multiply with W, add B, and apply the nonlinear activation function, but now I use it as an increment. So what I do is, to go from one layer to the other, I take my previous result, my xk, and then I add with a small delta, or small, large, whatever you want, a delta, I add this, what I had before, okay? This transformation of x. By just rewriting, I can rewrite it like this, right? This is still okay, so I can just take this to the other side, rewrite it like this. So what? Okay, well, what is that if you now remember back, if you don't remember anyway, what the definition of a derivative. If I now think of the network really preserving the dimension of x, so my matrices are square matrices, and when I go from one layer to the other, my x vector is always the same dimension. So when I take in an image, out comes an image of my network. I now look at an image-to-image network, for instance. Then I can look at the limit of this equation for delta going to 0 and k going to infinity, which gives me, instead of this difference here between two consecutive layers, gives me the derivative of x dependent on time, where time is now my layers, is now going through my layers, okay? So instead of this discrete way of going from one layer to the other, I now have an infinite number of layers, and I go through them via this evolution equation. It's now called an evolution equation because I'm changing my input vector x at time t equals 0, let's say, by going through this evolution that is given here by the right hand side of this equation. And the nice thing is, these type of dynamical systems, these type of evolution equations, they appear in all kinds of scenarios. We mathematicians, we applied analysts, let's say, we actually know these equations very well, and we have a huge toolkit to actually understand them. And also by thinking of them as an evolution, we can actually now think of looking into what is happening in this neural network and trying to find out if we can do anything with this. So again, in the same way as these different type of simulations show you the different axes when x is following a certain right-hand side, I can think of this also for the network. And in the same way, I can plot what is happening, for instance, if I'm training a neural network to take as an input what we have seen before, these point clouds of two classes, and I train the neural network now to transform them into something that can be nicely classified with a linear classifier. Okay, where the linear classifier here is indicated by this line here. Okay. And so what you should see here is just plotting the x while going through these layers. Okay, this is cool in a way, but why am I so excited about this? The nice thing about this is that once we have such a continuum model, we have such a representation that we mathematicians can somehow analyze, understand, tweak, we have a way to use this knowledge to change things in the network in a systematic manner, to make it, for instance, more stable, to make it more controllable, maybe to have these dynamical systems in nature, for instance, they have certain things that they preserve, right? They have certain features of solutions like volume preservation or things like this. These are maybe ways for us to be able to also insert these type of features into neural networks. These are ways maybe to make neural networks safe, and so on and so forth, efficient, and so on. So this is one way, right? There are various different ways how mathematicians think about this, but this is one way. And I hope that this somehow gave you one little bit insight into what is actually under the hood in deep neural networks, and how mathematicians, one way of how mathematicians are thinking about this. So mathematics offers a powerful and rigorous toolkit to attack problems in deep learning. Understanding deep learning is mathematically though super tough, and there are more open problems than solved ones. And why we are so all excited about this is because there are many applications where deep learning works so well. And so also within mathematics even, people are using deep neural networks to solve, for instance, differential equations. So with that, I thank you very much for your attention. Thank you.